Newton's third law is mainly talk about two forces, action and reaction force. Okay, the key thing between them is that they are equal in magnitude, but they're opposite in direction. And another really important concept is that the two forces, the action and reaction force, are actually not acting on the same object. What that means is, say for examples, I have a person A and I have a person B. If I say that the action force is person A push to the right at 10 newtons on person B. If I were to draw the free body diagram, is this force acting on person A or person B? Person A pushes 10 newtons to the right on person B, right? So it's actually a free body diagram that's actually acting on person B. So if I were to draw a free body diagram for person B, I actually have this force that is going to the right that is 10 newtons from person A acting onto person B. What would the reaction force be? The reaction force is actually right now person B, it's actually being pushed 10 newton, but this time to the left on person A. That is the reaction force. So I would not come and draw a 10 newton acting on person B because it's not acting on person B, it's actually acting on person A. So what that means is I don't have this. Oops. Okay, I actually would now draw a person on person A. If I were to draw this, it's actually acting on person A that I have 10 newtons that is going to the left. Okay, so that's a key concept. Okay, so it's not acting on the same body. Even though the action-reaction force is the same opposite direction, if you analyze it, it's actually on two different objects. So this example, tractor exerts a force of 2,000 newton west on the trailer. So to understand it first, I think it's good to draw a free body diagram for each of them. So we will have a free body diagram for the tractor and a free body diagram for the trailer. Okay, so tractor exerts 2,000 west on the trailer. Does it make sense that it is the trailer that is feeling the forces and it's going 2,000 newtons west? So something like that, right? And this is the action force. And so does it make sense that when the tractor is pulling, the trailer is feeling a pull towards the forward direction? But at the same time, the tractor should also feel a drag that is going to the opposite direction, being pulled backward, and that is your reaction force. So the reaction force is now actually acting on the tractor, which is the same amount of force, the equal and opposite force, but now acting by the trailer. And this is your reaction force. So to write out the statement, you don't always have to draw a picture. I just wanted to make sure that when I draw the picture, you have a better understanding of the key point. The action-reaction force are always the same magnitude, but opposite in direction and always acting on two opposite thing. Okay, so let's write this properly. The action force is the tractor. It's exerting, it's pulling 2,000 newtons west on the trailer. And to write the reaction force, basically, you can just very easily take the two objects, swap the location, and change the direction to the opposite. Okay? So instead of the tractor, what happened is now the trailer is now pulling the same magnitude, but opposite in direction, so it's towards the east direction on the tractor. So that's how you write the action and reaction forces. So we're now talking about a ball hanging on a string attached to the ceiling, and they want to describe all the action and reaction force. It is helpful to draw, first of all, the free body diagram of the object. So I got a ball, and I have a FG that's acting on it, and I have an FT that's acting on it, which is the force of tension along the rope. So let's take a look at the FT at the top. The action force is this upward force that's acting on the ball, and this is going to be the string is pulling upwards. It didn't give you a magnitude of number, so I'm just going to say the direction on the object, which is the ball in this case. And then let's take a look at the bottom here. The action force, now we're taking a look at this FG. So the earth is pulling downwards on the ball. Those are the two action forces that are actually keeping the ball balanced, the forces balanced. So now let's take a look at the reaction force. So just now we already talked about, you basically swap the object and you change the direction. So the ball at the same time is pulling downwards on the string, and the ball is pulling upwards on the earth. Question asked now, explain each of the event in terms of Newton's third law. So on a quiz, if you have a question like that, it's always a good idea to state the law, especially like sometimes they're not as nice and tell you, hey, explain using Newton's third law, and hopefully you get that this is a third law question. But as long as it's mentioned it, you should mention the law. So I'm not going to do every single one of these questions, but I'm just going to do part A at the bottom. So it tells you a swimmer is moving through the water. So you would probably start off with, according to the Newton's third law, for every action force, there is an equal and opposite reaction force. So let's think about the swimmer. So the swimmer is pushing backwards to the water. And that is the action force. And the reaction force is the water is now doing the opposite thing, is now pushing forward on the swimmer. And that's why the swimmer can now go forward, causing the swimmer to go forward. Okay, notice success criteria. Let's just quickly talk about that. Okay, you always state the law, right? Like whenever we give you guys application question, you always go back to the physics. Okay, and then follow the format, right? So I got the swimmer and the water and the backwards. So then I rewrite it. And then for the reaction force, it would be I swap these two and I change the direction the same way that we've been doing that. Okay, so that's your second mark right there. Okay, so after we've been through Newton's first, second, and third law, I just want to take the time and do a little bit of summary of all the three laws and kind of the general methods of solving problems. So the summary of Newton's law. Okay, first law, it's the big word is inertia. And the inertia has two big parts. we're assuming that there's no external unbalanced forces. And if that's the case, your acceleration is equal to 0, or vice versa. If you don't have an acceleration, we also can assume that the net force is 0. And when they mention the acceleration is 0, you can assume that the object is either at rest or that it is traveling at a constant velocity. Okay, second main point is the Newton's second law. Second law has the equation F net equals to ma. If I do have a forces that are not balanced, then it's telling me that it will be accelerating. And through the acceleration, sometimes with these types of problems, the acceleration will be related to the high fives, solving for A. And then the F net is through calculating the net force along X and the F force along the Y. And today we talked about the third law. The third law is the action and reaction force. And the general format of solving all these types of problems are the same. Okay, so I'm just gonna do a little format thing. I'm just gonna add a new slide. In terms of format, with these types of dynamic question, unit 2 dynamic, the reason why objects are moving a certain way, we always first off start off with the free body diagram. With the free body diagram, we would include all the forces that are acting on the object. We always would draw a direction to indicate the direction of the net forces, therefore telling you the directions of the acceleration. And we would break it up into the XY axes. Second step is we would analyze the force using F net along the X. You would be something minus something, usually the positive side of things. Like we got the positive side of things, which is like kind of the direction of your acceleration, and it makes it equals to ma. And then we would do the same thing along Y. It is something minus something or adding whatever equals to ma. And one last thing that is really important that we want to talk about is the fact that between the X and the Y, the most important thing is at least one of the acceleration, whether it is the X or the Y, either, okay, at least one, sometimes both, is equals to 0. Because the way that we set up the format of the X and the Y, we would always make sure that we would not have acceleration along both axes. It might not be as important in the grade 11 courses, but in the grade 12, when you're dealing with free body diagram that are moving on an inclined plane, you have to be aware of that. So we're starting now in grade 11 to get the format going. Two skaters are standing on ice facing each other. Skater 1 pushes on skater 2 with a force of 70 Newton to the east. Assuming no friction acts on either of the skater, the mass of skater 1 is 50 kilogram and the mass of skater 2 is 70. First thing I need you to do is I need you to fix my signet. Can you put that this is 70.0 kilogram, this is 50.0 kilogram, and then that is 70.0 newtons. Okay, so state the action and reaction force. So part A asks for what is the action and what is the reaction force. The action force is saying that it's skater 1 push on skater 2. So skater 1 push 70 Newton east on skater 2. The reaction forces, remember we talked about We take the two objects, we swap it, and we change the directions to the opposite. So meaning the reaction force is skater 2 is now pushing the same magnitude but opposite direction. So if it's east, now it becomes west on skater 1. Part B. Draw the free body diagram for each skater. So I got skater 1 here, skater 2 here. I always do find it useful to put their masses right on top so that I'm organized in terms of my given list and stuff. So I know skater 1 is 50 kilogram, and I know skater 2 is 70 kilogram. Draw my free body diagram. So the action force, I'm going to color code this. So I'm going to use the red to represent the action force. Skater 1 push 70 Newton east on skater 2. So meaning I am acting this force on skater 2, and it is going 70 Newton to the east. You can say FA, or you can just put the 70 right on it. Okay, and then I'm going to use a different color. I'm going to use blue. Now I'm going to draw the reaction force. The skater 2 pushes 70 west on skater 1. So meaning it is acting on skater 1. Skater 1 is feeling the force, and it's going backwards towards the west. FA is 70. And at the same time, don't forget we need to finish off the free body diagram. There are other forces. There's force of gravity that's acting on both of them. And it's standing on ice, so I also have force of normal that's holding it upwards. It tells you to ignore friction. There's no friction in this case, so that's pretty much all the forces that are acting on it. So describe what would happen to the skater. We do see a net force. So we see a net force that's going towards the west direction for the skater 1. And we do see a net force of going to the right for skater number 2. Question C. Calculate acceleration. When it involves acceleration, we're going to have to find the F net. So for skater number 1, analyze the forces along X. I only have one force, so F net X is equal to, I only have one of the force, so it's FA. F net equals MA. And in this case, FA is 70. And the mass of person number 1 is 50. And A is my unknown. Punch it in the calculator. So it worked out to be 1.4 meters per second squared. Check the number of sig digs. I know I changed the question on you, so we have 3 sig digs in total. So I'm going to have to stick a 0. Meters per second square, and take a look at the direction is towards the west direction. So make sure you got all these covered. Do the same thing for Y. For the other part, for part 2. Along X for part 2, I have one force in total. So F net X is equals to FA equals to MA. And net force is 70. The mass is also 70. So A worked out to be 1 because I need 3 sig digs is 1 meters per second square. And the direction in this case is going towards the east.